I think the interesting part of the binomial theorem topic is having a look at these relationships between the coefficients that we can come up with just by a little bit of manipulation. It all starts with the binomial theorem, and by the binomial theorem I'm meaning the standard one of just 1 plus x to the power of n, which in some notation there's our general term nckx to the k, and of course we go from 0 to n, and if we expand that out we get of course nc0, nc1x, nc2x squared. Somewhere in the middle there'd be a term nckx to the k, and at the end ncnx to the n. If we were to find the value of this expression here, k equals 1 to n of nck. So in other words, nc1 plus nc2 plus nc3 all the way up to ncn. I say all of these things start with the binomial theorem. So I write it down. And then I have a look at what I got and what I got to get. And there's usually 3 ideas. This uses the first idea of just a substitution. If I substitute a value in for x, can I get what it is that I'm looking for? Now, in the sum, I've got nckx to the power of k. What I want has got no mention of x whatsoever. It's just got nck. So what could I substitute in for x to make it, well, look like it's gone away? What are we substituting in? Anyone?
1.
Why 1?
Because 1 to the power of anything is still 1.
Very good. So if we do x equals 1, then on the right hand side we get 1 to the power of k, which is always 1. And on the left hand side I get 1 plus 1 to the power of n. So I now have 2 to the power of n is from k equals 0 to n of nck. Just as a sideline, what that basically means there, what we've shown there, is any row in Pascal's triangle, all the terms will add up to 2 to the power of n. However, for our question, we don't want from 0 to n, we only want from 1 to n. So what I'll do is I'll change that sum to be 1 to n, but then I'll say, oh, and we've got this additional bit, nc0. But we know nc0 is always equal to 1. So I can subtract that from the other side, and I get an answer, 2 to the power of n minus 1. Now this time, they're saying, hey, I just want the odd ones. What about if we only added up the odd ones? So again, let's start with the binomial theorem. And I'll expand it out so I can see the pattern. Now I've got all of them. If we, like we did with the last one, let x equals 1, we know the x's will go away, but I've got all the terms there. But now what I'll do is substitute in negative 1. And that'll now mean every second term will be negative, because we'll have negative 1 to an even power, then negative 1 to an odd power, then even, then odd, and so on and so on. So I can now eliminate the even ones by using simultaneous equations. So if I subtract, I'll get 2 to the power of n is 2 lots of nc1 plus 2 lots of nc3, 2 lots of nc5, and so on, and so on, and so on. If it was the even ones I wanted, instead of subtracting, I'd add the 2 together, and then the odd ones would cancel out. We end up with 2 to the power of n minus 1, because if I divide both sides by 2, I'll have my odd ones, nc1, nc3, nc5, and so on. So again, an example of well in this case, 2 substitutions I had to use. Sum from 1 to n of k times nck. Okay, binomial theorem. What's different with this one? I guess, yes, if we substitute x equals 1, but we've got k out the front. So now we have to think, well, what mathematical operation would bring k to the front of this? Calculus. If I differentiate both sides of this, then the left-hand side will become n outside of 1 plus x to the power of n minus 1. But now my general term, k will be out the front and the power will be k minus 1. So now we can do our substitution. X equals 1, that'll make the x go away. once again, I've got 0 to n. They want 1 to n. Well, actually, when I substitute in 0, I'll get 0 anyway because it's k times it. But on the left-hand side, we've got n times 2 to the power of n minus 1. So there's our answer. So that's the second idea. Rather than just a straight substitution, use some calculus. All right, now it's starting to look a bit fancy. All right, let's write it out again. This time, what's the difference? Well, I think it's kind of obvious what we're going to substitute in for x. Well, maybe not as obvious, but I've got x to the power of k in the binomial theorem. I've got minus 1 to the power of k in the expression they want. So I'm probably going to do x equals negative 1. But I've got k plus 1 on the bottom of the fraction. How do we get k plus 1 on the bottom? Yeah, once again, we'll use calculus, but this time we'll integrate. So if I integrate both sides, but of course we're going to get a constant. Now I've called it capital K because I've used C in combination, I've used little k, but whatever constant you want to use for constant. All right, so we have that expression. Can I work out the constant? Well, to work out the constant, I'm going to let x equals 0 because on the right-hand side, every term will be 0. Because if I make x equals 0, I'm saying sum from 0 to n of nck times 0. Well, so I'm going 0 plus 0 plus 0 plus 0 plus 0. On the left-hand side, I'll get 1 over n plus 1. So my constant must be negative 1 on n plus 1. So I can work out my constant that way. Now I'll let x equals negative 1. So I'll get the negative 1 to the power. Now let's have a look at the right-hand side. Have we got k equals 0 to n? Yes, that's what we want. nck, good. K plus 1. Looks like we've got everything we need on the right-hand side. So now we just have to tidy up the left-hand side. 1 minus 1, well that's 0. So it's just going to be negative 1 on n plus 1. I'm looking at it. Oh, hang on a sec. Oh no, it's not quite the same, is it? Look at the question. It's to the power of k. I've got power of k plus 1. So I need to do one final thing. Change it to power of k. Divide by negative 1. It's like saying, hey, how do I get from 2 cubed to 2 squared? Divide by 2. So I want to reduce that power by 1. I'll divide by negative 1. So it's actually positive 1 on n plus 1. Okay. Now for the third idea. The third idea then is where we compare particular coefficients. So we might say, hey, let's have a look at the coefficient of x squared, or let's have a look at the coefficient of x cubed on both sides. So that's the third idea. We have 1 plus x to the power of n times 1 plus x to the power of n is the same as 1 plus x to the power of 2n. Well, that makes sense. Add the powers, n plus n is 2n. So using that idea, we have to show the sum of nck all squared, going from 0 to n, 2n factorial over n factorial squared. All right, so once again, we'll start with the binomial theorem. I'm going to expand it out. Okay? It's giving me the hint we're going to compare the coefficients of x to the power of n on both sides. So let's look at the left-hand side first of all. 1 plus x to the power of n times 1 plus x to the power of n. I've written my expanded version out times I've written the expanded version out. Which combinations would create x to the power of n? So nc0 would have to be multiplied by the ncn x to the power of n in the other one. So I've got nc0 times ncn x to the power of n. The nc1x would have to be multiplied by the ncn minus 1 x to the n minus 1. So I get nc1x times ncn minus 1 x to the power of n minus 1. The squared would have to go with n minus 2. And so on and so on. So the cubed would go with n minus 3, power of 4 would go with n minus 4. And as we keep going down, that x to the n minus 2 would then match up with the x squared and the next one. The x n minus 1 would match up with the x, and the last term, x to the n, would be matched up with the nc0. Okay. So looking at the coefficient, let's not worry about the x to the power of n, we're only interested in the coefficient. I've got nc0 times ncn, nc1 times ncn minus 1, nc2 times ncn minus 2, so on and so on and so on until I get to the n, ncn times nc0. But we know Pascal's triangle is symmetric. So nc0 and ncn are equal. nc1 and ncn minus 1 are equal, and so on all the way down. So I could rewrite that as nc0 squared plus nc1 squared plus nc2 squared up to ncn squared, which is the left-hand side of what we're trying to prove. So I've got that. Okay, I know looking at it that way, I get the sum from k equals 0 to n of nck squared. So now let's have a look at the right-hand side. Let's find the coefficient of x to the n in 1 plus x to the 2n. Well, that's just, again, an expansion, but instead of n, I've got 2n. So it would go 2nc0, 2nc1x, 2nc2x squared, and so on and so on and so on. Somewhere in the middle, there'd be a term that goes 2ncn x to the power of n. So in that whole expansion, there's only one term that's x to the power of n. So the coefficient in the right-hand side would be 2ncn. Okay, but we know those two expressions were equal. Therefore, the coefficients of x to the power of n must be equal. So because we know they're equal, those coefficients must be equal. All right, well, the right-hand side, that's not quite what they asked us to prove. Let's put it in the factorial notation. Factorial notation will become 2n factorial over n factorial, n factorial. Numbers on the bottom must add to give the top. Well, n factorial times n factorial is n factorial squared, and that's what they were looking for. So these are the fun ones of the binomial theorem. You get some lovely questions. So what I've got for you there, 5 F's from the textbook. I've also put a worksheet in there which sort of goes through some of these ideas as well. You might like to look at that first or after the exercise, up to you. But then I've also put in, I've gone through some past Catholic trial papers and independent trial papers and pulled out all the different binomial theorem questions there, going back to, I think I went back to about 2011.